time I've been in Berlin, and I came in 1991, and it's fantastic to see the things that have been going on in this city and to be in this great university. So I'm going to talk about some work which is, I like to talk, when I give talks, I like to give talks about stuff I'm working on, which has the risk of being incomplete compared to finished papers, but it's more fun for me, and so I'm going to do that today, and hopefully it's not too half-baked, but it's going to be incomplete, and it's joint work with Ole Bandorf Nielsen, who's a Great Dane, and who works at Aarhus University. Okay. I'm going to talk about this paper came out from me trying to think through the connections between a literature that I knew very well and a new literature. Well, a little old. Some of it's old and some of it's new. And so I'm going to come at it from the perspective of someone who's been interested in realized measures, realized volatility, and other types of things. And then these of course estimate ex post variation of asset prices measured over a day or something like a day, so over some sustained period of time. And they're non-parametric, and they have been shown, as we saw in a talk, an elegant talk Andrew Patton gave this morning, they allow better forecasts of future volatility. So they've allowed econometricians to usefully think about harnessing high-frequency data for a number of different tasks, and that's been very exciting. And it's been exciting because it's of practical relevance. It raises a number of new econometric issues, and also it's mathematically challenging. So it's been an area where there have been a lot of great interdisciplinary research bringing some really smart people into econometrics for the first time, tackling some substantial questions. And that's been fantastic to see for us econometricians. And I think that there are still some open problems there, and areas for making contributions. So these realized measures can be made robust to jumps, noise, or effects, if you want to call them effects instead of noise, and can be multi-dimensional. And here are some examples. So there's literature on realized variance, which many of the people in this room have contributed to, and I certainly learnt a lot from people here. And also literature on trying to make these measures, change these measures to make them somewhat robust to different aspects of noise. And we've had quite a few talks about that too. An area that econometricians have really pioneered really is to think inside quadratic variation non-parametrically, to try to break up quadratic variation into interesting components where we think about jumps and continuous evolution of prices, and take that to data to try to think about, does that add to our ability to understand and to forecast? And again, many of the people who've contributed to that are in this room. And an area that I think, in addition, is quite interesting, I think it's quite interesting, is to look even further inside quadratic variation, into thinking about asymmetries in jumps, down jumps and up jumps having different properties, and so I've been interested in that with semivariances, and Kevin and Andrew in Oxford have been taking that in a forecasting context and showing that's really quite interesting, how some explanatory pair and forecasting future volatility. So there is a substantial literature, and I think those of us who were kind of at the start of that literature, kind of very proud of the not only empirical relevance substantial economic relevance, but the technical innovations that people have brought to bear, which in my view, those combinations is what econometrics is about. So I'm quite proud of that, and it's a very sustained literature. And I'm going to talk about another literature. And this other literature, I think, is an interesting literature which has old bits and some new sparkling new bits. And this is on estimating spot quantities. So I'll focus my talk on spot volatility, but it could be other types of spot quantities. And this was started in a pioneering paper by Foster and Nelson in Econometrica in 1996. And that paper is a very interesting paper to read because it's about daily data. It's not about high-frequency data. It's about trying to connect Garch models, which were the predominant way that econometricians at the time were thinking about volatility, to continuous time models. My interpretation of what we've done in the last 7 or 8 years is to move away from that framework and to address the continuous time models directly. Okay, and rather than thinking about things through a lens of a Garch model a priori. So there's lots of things in Foster and Nelson which, to a modern eye, a decade later or 1.5 decades later, looking at Foster and Nelson look a little odd. But there are aspects of that paper which are terrific, and I'm going to talk about them in my presentation. And also I'm going to relate it to some work that Dennis Christensen, who's also here, has published in a very, I like this paper very much, in Econometric Theory last year, which will be a kind of modern non-parametric kernel reinterpretation of Foster and Nelson with some twists. And there's also a paper which maybe people don't know so much by Fan and Wang, which is really doing very similar things to Dennis's paper. So I kind of pair those papers together. But I really like both of those papers. There are 3 papers to my knowledge which are unpublished in this area. There's a paper by Bandy and Reno and my colleague Shinkanaya and Dennis, which are related to this too. They're looking at spot quantities and thinking about the econometrics of that. And so I'll refer a little bit to their papers. In some way, they're kind of the next generation papers. And there's a poster here as well on that subject. So the economic motivation of this, so in realized things, the economic motivation is usually about risk management, also connection to option pricing, where integrated variance type objects are very important. The economic motivation for spot quantities is somewhat different, I think. As far as I can see, a lot of the motivation is in automated trading, high-frequency trading, which can have 2 very different, but really they're the same interpretations, which Joel talked about. You can think about them, and this is the nice one, you can think about it as minimizing trading costs, slippage costs, if you're doing portfolio analysis or whatever, if you're actually trading something. And the one which is a little bit more dodgy is you can think about it as doing statistical arbitrage, which was a little bit the focus, I think, of the previous keynote talk. So there are hedge funds which specialize in that. The most famous one that does statistical arbitrage is Renaissance. But I don't know anything about that. So I want to explore the connection between the realized literature and the spot literature. My main interest is in bandwidth. So you'll see that later. I'm not very interested in results that don't tell me anything about bandwidth. So, because I want to use these things in practice, and the most important thing in practice is bandwidth. At least to me, but for other people it's other things. But to me, whenever I do econometrics, I really want to take econometrics to the data. It's a theme of, it's what I think as econometrics is about. So what I'm going to do is I'm going to look at the special case, and some of the papers I've listed up here are more general. I'm going to look at the special case of localizing realized measures of various types to look at spot volatility. You can do better than that. You can use more sophisticated weight functions, and Dennis and Foster Nelson, these papers, they're much better than me, and they'll have insights which I think it would be nice to push some of my work that I'm going to talk about here in that direction. But hopefully I have some insights to that, and if not, at least I'll be able to relate these two things to you. So this is my intellectual framework. So I'm going to think about time only existing between 0 and 1, and I'm going to work with infill asymptotics, and so I'm going to have n equally spaced high-frequency observations. Now, there are a lot of people in this audience who will say I should be working in trading time, and I agree, and I could have done that, but I want to keep things simple here, and I agree when you take this stuff to data, it would be better to do things in trading time. But bear with me. I think it's interesting to have the clarity of equally spaced things when you think about theory, at least. So I'm going to have initially a Brownian semi-martingale stochastic volatility process here, what I call a Brownian stochastic volatility process, because it's driven by Brownian motion with a drift in here. I'm going to talk later on about jumps, so I'll be talking about estimating local things in the presence of jumps. But for the moment, to clarify, there will be no jumps. Most of my talk will assume that the volatility process is itself a Brownian semi-martingale. So it is itself a stochastic volatility model where presumably it has some mean reversion quantity in here. Again, at some point I'll allow jumps to appear in here, and it'll turn out it's irrelevant. Okay, but for the minute, just think of this as a continuous sample path process. Of course, it's a particular type of continuous sample path process because it's driven by Brownian motion things. So it's going to be, of course, continuous, but it's nowhere differentiable, and that's kind of important. And then we make some assumptions here, usual stuff, and my friends will be ashamed that I'm actually not going to discuss noise. So it's terrible. But everything I talk about, you can do noise, and I'm doing that, but I didn't want to present it here. So I'll talk about it another time. I said it was incomplete. So my interest is in estimating the spot variance or spot volatility, the square root of this. I'm going to have some high frequency returns, which I'll write this way. I'll have everything is equally spaced in time, and everything's going to be about a local window. So it's important to have this notation in your mind, and I'll try and use it. I think I use it all the time. So I'm going to look at data between time t minus u and time t plus v, where u and v are non-negative. Okay, so the obvious one would be the smoothing problem, where u and v would typically be taken to be equal. So you have data either side of the spot thing you're estimating. But also, just as important is filtering, where you just have data on one side. If you have filtering, then v is going to be 0. So all the results I give will cover filtering and smoothing automatically. And then I just have to make sure that t minus u and t plus v live in 0, 1. So there's a side condition on that. So what I'm going to do is I'm going to have a local window, I'm going to have a local sample size, which is just going to count up the data points in this interval. So they're going to be n observations in the interval 0, 1, and then they're going to be capital N observations in the interval t minus u to t plus v. So that's the number of points that fall in that interval. Okay. So this just gives you an example of this. So this is the kind of situation I'm going to work in. This is a simulated diurnalized Brownian motion, where the diurnal pattern in volatility space is given by this lovely pink dotted line in here, through here. And it's designed so that volatility roughly triples from lunchtime to the beginning of the day. So there's a very big diurnal feature. And that's what, of course, you get in real data. Okay? Later, so in this little simulation, that's the only form of time-varying volatility. Later on, we'll have some stochastic variation too, okay? And then this is the simulated diurnalized Brownian motion with a little added jump here, okay? Based upon 1,500 observations in this time interval. So this jump is a jump of 1 at time 2.5. Okay, and the volatility over the integrated variance over the day is around 0.3. So this jump is around 3% of the variation of the day. Okay, and what I'm going to do is, if I can get the computer under control, I'm going to estimate the spot volatility of this of the underlying Brownian motion. In a usual way, I'm going to localize realized variance, but I'm also going to introduce some localized versions which are robust to jumps. Okay, and I'm not sure how to do this. Okay, so, and then I'm going to test for jumps. I'm going to have a test for jumps which tests at every time point, is there a jump in the process? And this is my rejection region, and that's saying there's a jump around here. Now, it's going to be pretty low tech econometrics in that I'm going to use for a non-parametric smoothing kind of person. I'm using a rectangular window. You can do better, as Dennis has taught us in his paper, by, of course, using smooth weights which decay. I'm not going to do that here, so you could get more efficiency in things. I'm just going to focus on simple ideas here. But in potentially, you might be able to test for a jump at every point in time. This top line is the empirical quadratic variation of this process, okay, through time. So the realized volatility for this day is this value square rooted, okay. And then these are robust measures trying to strip out the effect of this jump, and I'll talk to you about them later. So that's the framework, and let's see that later. Okay, so this is now the obvious stuff. So I'm going to just define. I'm going to focus on actually these first two objects mostly in my talk. So realized variance is obviously sums of squared high-frequency observations. And I'll use this notation where the realized variance is calculated over the interval t minus u to t plus v here. So I'm going to study this, and I'm really going to just reinvent Foster-Nelson and talk through it, because I think it's very interesting. From a realized, if you come from a realized variance person and you read Foster and Nelson, you can reinterpret it and you get a very simple result, which people should know about but don't know about. So I'm going to take that result and then kind of just talk about it, and then I'm going to do power variation versions. So I'm going to look at not squaring but summing up absolute values raised to some power and then normalizing so that they make sense. And now power variation was where you have this normalization was there's some work early on. For example, Tim and Torben had a paper very early on at looking sums of absolute values of returns. But if you look at the theory, you need to normalize, and that theory was discussed in some papers I wrote with Ola some time back. And the advantage of this quantity is it has some robustness to jumps. The disadvantage, as we'll see, is it estimates the wrong quantity, which is a bit of a problem. But what we'll see is when you localize, it doesn't matter. Okay, so this will mean that power variation, when localized, is a really cool thing to do. And we'll see that if you localize, there's no need to do multi-power variation, which I interpret as a stochastic version of power variation. So I'll talk through that. You could also localize a Parsen kernel, which I've been playing around with, but I was too frightened to present that to you today because it's just, I haven't done enough about it, even for my standards, to talk to you about it. So I'm going to keep that in my locker. And likewise, you can localize semivariances. Of course, having robust quantities and noise is very important as you localize. So it's not that I'm saying this isn't important, it's just that I prefer to get it right before I talk to you about that. So the localized versions are, some of these quantities estimate the integrated variance. And so what we're going to do is just going to divide by the interval of time. Okay, so I'm going to call this estimator here localized realized variance. I'm going to call this quantity localized power variation, okay, which will estimate things I'll tell you about later. Likewise as localized multi-power variation, localized realized kernel. And I'll use this notation D for the time interval that's involved. And I'm just going to study the localized versions of these. So it's, as I said, it's very, very simple. Okay. And some of it's going to be related to Bandy and Reno's results, but I'm going to focus on the choice of U and V. I like limit theories that tell me something about this. Foster, Nelson, Christensen, and Fan and Wang look at RV type estimates. They're all based upon squares of returns. But they look at more general weight functions, so they don't just use rectangular weights, they use decaying weights, which are more efficient. The closest to my interest in terms of the asymptotics is actually the Foster-Nelson paper. I'll explain this in a minute. So as I said, our estimator is going to use rectangular weights. More general weights are interesting, and it would be nice to generalize what I do to it. The results should basically change very, very little, but there's some efficiency gains in terms of asymptotic variance, and there's a substantial empirical gain, particularly with edge effects. So as edge effects, as Dennis Christensen elegantly wrote in his ET paper, you can have some very nice kernel weight functions to deal with edge effects at the beginning and end of the day, and they're empirically very important. My rectangular weight stuff is pathetic at dealing with that. So that's particularly important there. But I'm not going to talk about it. I want to just focus on ideas, simple ideas. So this is the framework that we have. I'm going to localize, as I said, and then if for a cunning choice of U and V here, if you let those that window shrink into the half, you get this limit theory, and I'm going to explain this limit theory to you, where this comes from, if that's okay. So you get a rate of convergence. You can estimate this this spot variance, which is pretty interesting because that's a pretty rough object to be able to estimate, and you can estimate it at rate n to the quarter. Okay, this is where there's no noise, so it's kind of a slow rate. And there are two contributions. Notice the thing's unbiased, okay, to this asymptotic order. There are two contributions. One is a contribution that you will know and love from realized variance literature. There's something that involves the quarticity. In this case, it's the spot quarticity. And then there's a new term here, which in continuous time has got a very simple structure, and it doesn't matter if there's leverage or not. Okay, and it involves the volatility of the volatility. Well, actually, it involves the variance of the variance. Okay, so the square of this. Okay, so this basically is determining the roughness of the volatility path. The roughness of it makes a contribution to the asymptotic variance of the estimator, and I'm going to explain that term to you. This choice of how you shrink down balances off these two effects. The effect of having to estimate the volatility even if the volatility was constant, plus the effect of the roughness of the volatility path. Okay? And as I said before, this is you can find this result in Foster and Nelson. It's not like it's there with a big black line around it saying this is the result. But from a modern interpretation viewpoint, if you start from a realized volatility viewpoint, this is the important result in their paper, and it can be seen from their paper. So I'll attribute it to Foster and Nelson. If you subsample the realized variance, you would reduce this number from 2 to 4 over 3. Okay, but the other term doesn't change. Okay. And I'm just going to relate that to what happens when you fix U and V. For a fixed U and V, the classic central limit theory result is the following, which is you take the square root of the amount of data in that interval, you have an RV statistic, realized variance statistic, and you estimate the integrated variance. And then the central limit theory is mixed Gaussian, and the variance is the integrated quarticity over this period. Okay? What we're going to do is we're going to think about U and V getting small, and I'm going to give you an explanation of this result here. Okay, so I'm going to just go through why this result holds, because I think it's interesting. And then once you see that, everything else is obvious. Okay, so there are two aspects of this result which need illuminating when U and V go to 0. Okay. One of them is that I'm going to be studying the statistic not RV, but RV over the interval. And I need to control the fact that I don't want to estimate this. Okay, I want to estimate the spot variance. So I need to control the distance between this quantity and that quantity when normalized by this. Okay? And that new term, due to the integration of the spot variance, is going to deliver an extra term in the asymptotic variance. Okay. So they're going to be two distinct pieces: the usual RV piece plus the variation in the path of the variance process. So let's do that. So the first term is just a rewrite of what I just had, and then you get the usual term. So if you're happy to estimate the integrated term, you would just get this type of term. Okay? But what's important, it's very exciting, this computer. What's important is to control this term here, caused by the roughness of the variance process. And the roughness of I may have to use this, which I hate doing, then I'll have to look away. It's very tempting to point this here, but it doesn't entirely work. So let's see. Okay, I'll try and, I'll use this. Maybe if I use this, that doesn't work. Okay, so let's use this very gently. So I'm going to use this quantity here, and I want to just study this, because I think this is really good fun. So this is the amount of data minus the integral and the spot term here. So what we need to do is to study integrals of the difference between the volatility. How quickly does the volatility move around? And locally, the stochastic variance process behaves like a stochastic volatility process with no leverage. So you can think of this as an integral of an integrated process. And so it behaves like because the volatility has got the variance process has a volatility, it behaves like the volatility process times an integral of Brownian motion. Okay, that's how this thing evolves. And it evolves both in the future and in the past. Okay? And that thing, of course, is Gaussian. And it contracts at rate v to the minus 3 over 2. Okay? And so this is the relevant central limit. This is the relevant thing that you need to know, is that when you normalize it, it's normal 0 with a variance of 1 over 3. Okay? And so it's then obvious that that's the central limit theory. Okay? So you just need to know what you already know, plus this smoothness result, and you get Foster and Nelson. And what's cool about thinking about it like this is that this term will be the same whether or not you use realized kernels, power variation, or anything else that estimates integrated variance. You'll always get a term like this. What the other terms will determine is this term here. Okay? So I call this a wide central limit theory. So if U and V contract at rate n to the minus a half, you get this central limit theory. And this tells you basically how to choose the bandwidth. It says you can minimize the variance of this object by selecting C2 and C3. So that's rather nice. It's a self-contained limit theory. Then there's what I call a narrow version. These are where your intervals are smaller. You contract them in at a smaller rate. And because you contract them in at the smaller rate, this second term disappears. Okay? So I'm going to contract them in by dividing by the log of n. And this was the approach of Fan and Wang. And it's also written in a different way, the approach of Bandy and Russell and Dennis Christensen in their papers. And when they do that, they kill this extra term. So what they get is narrow intervals, and their central limit theory has this attraction that it doesn't depend upon really nasty objects. Because you think about trying to estimate that quantity. Okay, so I'll do that later on, but it's pretty tricky. Okay, so this is a very simple object to implement, but the central limit theory tells you nothing about bandwidth selection. Okay, so this one is more informative, but very difficult to use in practice. And this one is totally uninformative, okay, but extremely easy to use in practice. Okay, and this compares to the central limit theory that we know already about integrated quantities. So let's see what's easy and hard about this compared to what we standardly do when we estimate things over a day. Okay? When we estimate things over a day and want to construct confidence intervals, we have to estimate nasty objects like the integral of the quarticity, and everyone hates doing that because it's very difficult to do it. Okay? This is much easier. There's nothing there to estimate except for the thing you're estimating already. So that's nice. This one replaces this difficult task here with another difficult task, perhaps harder, estimating this quantity up here. Okay. So you can find these results in previous papers, but it's much nicer, these results, if you take the log. So if you use the narrow intervals, you get this is the central limit theory for the log. Okay, and it's really nice because it's pivotal. Okay, so you can estimate the spot variance if there's no noise, and you can get you get a pivotal central limit theory. There's nothing to estimate here. Everything's known. Okay, and that's really nice. And definitely working on the log is very, very attractive. And the wide version of it, if we reparameterize this, so this is now going to be the volatility of the log volatility, then you get this nice central limit theory, which doesn't depend upon the level of volatility, but depends upon the volatility of the log volatility process. Okay. Which you might think might be not too variable, actually. So now let's talk about bandwidth. In the wide case, it's easy to see how you minimize the variance. You minimize the variance of the bandwidth, minimize the variance of the estimator by selecting the bandwidth, selecting C2 and C3, and that's easy to see that there's just a constant times, depends upon the inverse of the volatility of the volatility. And these optimal bandwidth selections appear in Foster and Nelson. And they take these optimal bandwidth selection to the data using daily observations. Okay, and later I'll use them on high frequency data. And then there's the narrow version, where you need to choose a bandwidth. What I'll do is I'll estimate these C2s and C3s, and I'll use them, but then divide by log n. Okay? What I can't do is minimize the mean square error or do cross-validation, because that will lead to, in effect, using this type of limit theory, because this minimizes the variance of the estimator. Okay, so you can't minimize the variance of the estimator, because then, in fact, you'll be back here. You'll just lie to yourself in the confidence intervals that you generate. I'll also try, in my selection of bandwidth, I'll try to avoid silliness. So silliness is where you go through a period of time where the volatility becomes zero. You know, in which case it says choose an infinitely large bandwidth, which is just stupid, because, you know, at that time that might be zero, but over some sensible period of time it's not. So I will always say that I'll add a term here which says never use more than 10% of the day's data to estimate this. Okay. Just to link this into non-parametric density estimation. So if the volatility was non-stochastic and twice continuously differentiable, then you can think of this problem basically as the same as non-parametric density estimation. Then if there's no diffusive component, the optimal way of choosing these intervals is to allow them to shrink at n to the fifth. And then you get a rate of convergence of n to the 0.4. Far more precise estimates in that case. And that's exactly the same as kernel density estimation, the standard way of doing kernel density estimation. And that's achieved because microeconometricians typically assume that their densities are twice continuously differentiable. Okay, so it's just done by assumption. Now, I had a very interesting conversation with Wolfgang last night about this, and he told me that serious microeconometricians wouldn't do this, and that they would not make this mistake. However, every microeconometrician I know who's clearly in the non-serious case makes this assumption. And of course it's not driven by microeconomic theory. There's no microeconomic theory that tells your densities are twice continuously differentiable, as far as I know. And so this is just by assertion. It could be entirely incorrect, undermining the entire empirical work of the profession in the last 10 years. So I think it's unwise for us to make that assumption. So it's better for us to use this continuous time version. In the case of filtering, you get a different rate of convergence in this case. So in rate of filtering, if you have twice continuously differentiable stuff, then you get an n to the third rate of convergence. Notice when you have diffusive volatility components, then your rate of convergence is always n to the quarter, whether or not you're doing filtering or smoothing. It doesn't make a difference. We also have an argument that says if you add jumps to the volatility process, whether or not they're infinite activity jumps or not, then it makes no difference. The jump component, the jump impact on the integrated difference between the volatility is of lower order. Okay, and so all of our limit theory would go through, even if there are added jumps. Indeed, the narrow theory, where you're taking n to the half divided by log of n, doesn't rely on having a Brownian component in the volatility. If it was a pure jump process, the volatility process, then this limit theory would still go through. The wide theory needs a Brownian motion component to do it. So, I also talk about the bias caused by deterministic components if you use these diffusive models, and I add that to my bandwidth selection. So because we've got these really strong diurnal features, I want to make sure that they're not going to create too much bias. So even though they're asymptotically negligible, in finite samples I'll care about them and put them into my bandwidth selection. So I do that here. Okay. So this is an example of the kind of simulations I've been running using these diurnal features. I'm afraid I didn't use Joel's diurnal exponentials, which I learned about this morning. I used a fourth power to do kind of the same thing, so I apologize to him for this, but don't think he cares. Right. This is going to be a very rough volatility of volatility. So it's geometric Brownian motion. The volatility is going to be a diurnal feature times geometric Brownian motion. This is the sample path of the geometric Brownian motion here. So it's moving around really a lot compared to the data we see. And these are different estimates of the spot variance on different days with these diurnal features going on. And these are the difference between the log estimates and the true value of the spot variance through time. And so if you have enough data, you can actually estimate these things. Okay? There is a question if we have enough data, so I'll come on to that later. So in order to be able to implement the wide intervals, you need to estimate the volatility. I'll use a Silverman type plug-in approach to do that, to give me a rough estimate of a lambda. To avoid diurnal features, what I'll do is I'll assume the volatility follows a geometric Brownian motion where the volatility is lambda, and then I'll look at the change in the daily change in the log of the estimated spot variance process. And that should be the daily change in the actual log variance plus an error term, which is going to have an MA structure. So I can then estimate lambda off this, and I've done that in practice. I've used a little kernel to do that, so it's easy to do. So there are lots of assumptions going on here, but I just need a rough estimate. I don't need it to be true. It's going to determine the constant in front of all these bandwidth selections. Okay. So you can do the same idea as I've done here for multi-power variation. It's exactly the same. You just have a different constant in front of here. Okay. So the second term is the same as before. So I'm not going to talk about that. What I'm going to talk about is power variation. So power variation is not being used a lot in financial econometrics, but I think if one's interested in spot things, it should be. So this is a localized version of it's going to be a localized version of sums of powers. And this is the central limit theory for it here. So what this does is estimate for the rth power the wrong object. It estimates the integral of the volatility to the power r. Okay? So that's why econometricians in realized land haven't been using this quantity, because this isn't integrated variance. Okay, so it estimates the wrong thing. And that's why we develop multi-power variation to overcome that. But when you localize it, that's not too much of a problem. So in terms of these wide intervals, this is the central limit theory for spot. This is the central limit theory for localized realized power variation in here. And it looks much better when you do the log scale. So you take this power, and then if you rescale it, repower it, it estimates the spot variance, obviously. And this is the thing in here. So this is the same as before, this is the same as before, there's just a constant in here. So the log version of it is like this. So the narrow version is like this, where you divide by log n, and again it's pivotal. So it has a pivotal distribution. And this is how efficient it is. So this estimator is an estimator of the spot log of the spot variance. This is the constant. This would be 2. I'm going to plot this quantity divided by r squared. That would be 2 in the case r is 2, which is known to be the most efficient thing. So that gets you this quantity here. And as you move away in either direction, you lose efficiency. Okay, and but you don't lose it very much. So this number goes up to about 2.25 when r is 1. So remember, in by-power variation, this number moves from 2 to 2.6. Where you use r is equal to 1, it goes from 2 to 2.25. So when you use spot quantities, the loss in efficiency by not using r is 2 is much less than it is when you use integrated quantities. You can do bandwidth selection, which depends upon the value of r. In the same way, it's obvious what you do, just as before. And now you can think about jumps and power variation. So can we estimate the spot variance in the presence of jumps? So this will be, so it's well known that the power variation object is robust to jumps for fixed u and v. This should be sigma u to the power r. There's a typo here. As long as r is less than 2. Because each jump is scaled by n to the 1 minus r over 2. And it turns out power and multi-power variation work in the same way. So in power variation, you scale jumps by order 1 over n, 1 minus r over 2. In multi-power variation, you scale returns, absolute values of returns by a stochastic order of 1 over n, 1 minus r over 2. So power variation is always going to be better to do. So now let's think about localizing this quantity. If we localize the power variation object, you get n to the half times this power variation over a constant. So jumps are going to die not if r is less than 2 in the integrated case, but r has to be less than 1. So if you're estimating spot quantities and you want to be robust to jumps, you need to take r as less than 1. And if you want it to have no impact on the distribution, you must take r as less than a half. Okay, so you're taking sums of the absolute values of returns to the power, say, a third. Okay, and then you're localizing that, and then that will be robust to jumps. But isn't it cool that you can estimate the spot variance in the presence of jumps? So likewise, if you can do the same type of thing with the narrow method, where you're dividing by log n. It turns out narrow methods are going to be less robust to jumps than wide methods. So if you take the interval over shorter periods of time, it'll be more sensitive to jumps. Okay. So this suggests taking This suggests that you can use this to test for jumps. So in wide intervals, you have this limit theory. Narrow intervals, you have this limit theory. So it suggests looking at the difference between the spot estimator based upon a low power of r and the estimator based upon r is equal to 2. If you use the narrow intervals, you get a pivotal statistic. So you just compute this, take away the previous estimator, and there are no nuisance parameters. There's nothing to estimate on the right-hand side. It's just a constant. Isn't that cool? There's no quarticity stuff going on. You just look at the difference of two estimators of the same object. This won't be robust to jumps. This will explode. If there's a jump, you square it and divide by the interval that goes to 0. Then the localized realized variance goes off to infinity if there's jumps. Okay, this thing just converges to the log of the spot variance. So if there are jumps, you'll get a negative drift at rate n to the quarter log n. So this test statistic will just go off to minus infinity as n increases, and this gives you this in principle gives you a test for jumps for every value of t. The test will be independent for different values of t as long as the blocks are not overlapping. So you have very simple theory for that. So this is just a simulation. It's the same simulation as I gave you before. So this is where I'm going to use n is r is a third as my robust measure, and my robust measure is estimator of the spot volatility, sigma t, is given by these dotted red line here. Okay, and the dirty green line here is the spot, is the localized realized variance, square rooted. Okay, so this is the one that's going to have a jump in it. Then it's jumping up, corresponding to this jump here. Okay. The blue line is the r is equal to 1 case. Okay. These are the integrated versions of these objects. So this is the empirical quadratic variation on the top line. This is the estimator of the quadratic variation of the continuous component on down here. Okay. And this is the rejection region for a test. Notice, of course, the rejection region. This is a 99% test. And the rejection region is just a constant, okay, because there's nothing to estimate. So that's a smooth case. You can also do filtered cases. So this is the question of I'm looking as data comes into my computer, and I'm trying to work out if there's been a jump as fast as I can. Okay. And that's this picture. So this is a filtered estimator of the volatility, and this is the effect of the jump. It's the same thing. This is the same data. It's just that I haven't drawn it with dots this time. I've done the nasty shortcut of lines, and that jumps up. Okay, and so I'm identifying in real time this jump. It's kind of interesting. So now you can take this to data. So Kevin kindly gave me some data. So this is the last working day of September 2008 on the S&P 500. I'm going to use 1 minute return data. So what I'm going to do is I'm going to do this in 2 stages. So I first of all use a fixed interval of time, which is I'm going to do smoothing. I'm going to use 10% before, 10% afterwards, estimate the spot variance, and then I'm going to run it through my algorithm to estimate lambda using a whole month of data, and then my estimated lambda I'll use to determine my window length for the real application. So it's been a 2-step procedure. So the estimated lambda gives me windows which are 2% of the day either side of each particular value of time. And this is the data. This is a pretty serious day here. So we've seen a 7% move at some point in the day, although there's a little bit of relief at the end of the day. It looks from the eye like maybe there are some jumps perhaps. Maybe there, these are the estimates based upon these different things. So this is the R is a third estimate, and this is the R is 2 estimate. Okay, and this is my jump test. It says basically there are jumps. There are a lot of jumps, and that's what I find with this test. So there are just jumps everywhere, and now, there are problems here. I need to realize kernel this, because I could be sensitive to noise. But this is my initial stuff. I just want to mention these ideas trivially carry over to the multivariate case. This is discussed in Foster and Nelson, but the results are once you have the continuous time framework, the results are actually very elegant and easy to understand. And they're basically just the same as the multivariate realized central limit theory plus the discretization error term, and that's easy to get. So they are very simple, and that allows you to have spot estimates and central limit theories for spot regressions and correlation type objects. So actually in my talk I've been much too positive about this stuff. I realized listening to myself. I'm very skeptical that this stuff works, by the way. So let me make some conclusions. So I know that it works on simulated data under what people regard as realistic simulations of data by the profession. Strong diurnality, big stochastic volatility effects. Okay? If you have a reasonable amount of data, you can estimate reasonably well the spot variance, and you can do jump tests. And I believe all of that is true. But I believe that there's a long way from that to taking it to data. Okay, because I don't believe these models work very well at very high frequency. So I just wanted to say I'm a little bit skeptical, as you'll see. It's from my conclusion. So in this presentation, I've tried to look at the connection between realized and localized realized quantities. I think with our knowledge on realized quantities, it's now easy to see a whole way of localizing objects which are interesting. It's straightforward to understand the difference between integrated and spot terms. And in particular, in this new world, power variation is a very attractive object. And it replaces multi-power variation. You don't need multi-power variation when you do the spot quantities. It's very important when you do integrated quantities. My general point is I'm quite skeptical that this estimation can be done usefully in practice, and that's why I'm trying to do this research. I'm trying to make up my mind whether or not you can actually do this in practice. I've convinced myself in the last few years that it makes sense to do realized things over a day. That works and it produces insights. I'm trying to work out for myself whether or not that's true when you look at spot quantities. And I have convinced myself to kind of base count 1. I've convinced myself that these methods work nicely in a simulation environment. It's not a toy simulation environment. Like some people simulate Brownian motions and say, I can find everything and estimate jumps and all these types of stuff. But I've got real diurnal features, I've got volatility moving around and stuff. It's a real, I've got a simulation environment with big data. Diurnal features can be overcome by these methods, to my surprise. I thought they would mess them all up, and that's not true. The methods are data hungry. I need to realize kernel these things, and maybe the rate of convergence just becomes stupid, so slow. The weight functions that Dennis Christensen has emphasized, I think their impact is not very much theoretically, but important practically because of end effects. And so I hope people will work on those problems some more, as Dennis has kind of led the way on suggesting that. So the end of my talk is I'm not there yet answering my own question in my own mind about whether or not this stuff works or not. And hopefully someone will be kind enough to invite me to give another talk where I'll be able to tell you about that later on. So thank you very much.